All right. Chat is here. All right. So it's really unbelievable to actually look at the pixel value of the grayscale value at this cell B and cell A. They exactly have the same brightness, same grayscale value. So A appears a lot darker than B, but if you just you can use Paint or other programs to actually get the pixel value at that location. And if you look at the pixel value at those, any value inside B and any value inside A, they exactly have the same gray values. So this is, but while we're perceiving luminosity, we also take surroundings into account. So perception is really something difficult to compensate all the time. All right, now let's take a look at our ray tracing algorithm. So let's start our first way to an attempt to see a virtual world. So I'm going to talk about the components, main components of a ray tracing algorithm, and we are going to start maybe deriving the equations today and maybe turn it into some code. So first of all, in order to take a picture of a virtual environment, we need to have a coordinate system. Okay, so the coordinate system that we're going to be using is the Cartesian coordinate system, which will have an x-axis, z-axis, and y-axis that are oriented with respect to each other like this. You could also have, for example, well, I mean, we usually draw it like x-axis to the right, y above, and z towards us, but you can rotate this, these three axes any way you like, and you will still have the same, a coordinate system. Okay, so for example, it could be like this. X could be, I mean, if I rotate it like 90 degrees along the z-axis, it could also be like this, right? So this is x. No, if actually this will be x, and this is y. This is z. So this is again a coordinate system. If we draw it like this, this is positive y, positive x, positive z. So this is like we need the coordinate system in order to use numbers to indicate position and geometry of objects. All right. So assume this is usually called the world coordinate system, or WCS in short. Okay, WCS, world coordinate system. So we have to have some world coordinate system with some origin, and also in this world coordinate system we are given usually in this world coordinate system 1, 0, 0 vector is the vector that sometimes we call this vector u in the positive x direction, and this is v in the positive y direction. It is 0, 1, 0 is the unit vector along the y-axis, and 0, 0, 1 usually indicated as w. So u, v, w. If you see these vectors, three vectors, they are unit vectors in the x-axis, y-axis, and the z-axis along the positive z-axis respectively. Okay, so first of all, we need a coordinate system. This coordinate system, I mean, how do you fix it, or how do you determine that? I mean, this is in most cases we don't actually indicate this coordinate system explicitly. It is implied. For example, if I say I have a sphere at 5, 5, 5, okay, centered at 5, 5, 5. When you say something like this, the indication of sphere center at 5, 5, 5 assumes a global world coordinate system that is something like this, and then you can put your sphere. Where is 5, 5, 5? 5 is here, so maybe let's put it in 2, 2, 2, so that it fits on this whiteboard. If you put it on 2, 2, 2, so it will be 2 units to the right, 2 units above and 2 units in this direction, maybe it's going to be somewhere centered here. So its projection, its center's projection is maybe going to be somewhere here. So if this is 2, this is 2 here, and this is also 2. So it's like, imagine if we had a light source directly above, it would cast a shadow on the XZ plane at this location. So, or if we had a light source here, it would cast a shadow on the YZ plane at 2, 2. So we can look at, talk about different projections of this sphere, but having a sphere centered at 2, 2, 2 is going to just place it at some position in the world coordinate system. So usually when you give this information, I have a sphere at 2, 2, 2, you imply a world coordinate system, and this 2, 2, 2 is given in your world coordinate system. For example, the center of the sphere could be at 0, 0, 0 in its local coordinate system, or also known as modeling coordinate system. For example, somebody may have modeled this sphere such that its center is 0, 0, 0. Okay, so before this sphere is put into this world, it may be placed in there may be some local coordinate system that it has. It has its own local coordinate axes, and it may say, for example, then its radius is 1. So a unit sphere centered at 0, 0, 0, and with a radius of 1. Okay, now, but when you imagine you have this sphere and you want to have 5 spheres in your virtual world, and this is your sphere model. In the modeling coordinate system, all of them are at 0, 0, 0 with a radius of 1. Okay, now you want to create your own virtual world with these spheres in different places, some of them big, some of them small, and located at different locations in this 3D world. How are you going to do that? What we are going to do is, we are going to, for example, if you want to place a big sphere to the right here, what do you need to do? You need to move its center to the right, make its center 5, 0, 0, or 5, 1, 0 if you want to put it a little bit above. So you basically change its center, you move its center, and if you want to make it bigger, what do? You scale its radius, for example, from 1 to 3. Okay, we are going to see these things later in the upcoming weeks. These are the things that I just did to create my virtual world in the world coordinate system. I applied modeling transformations. So I transformed my sphere in its local coordinate system. In order to put it into virtual world, I transformed it. I moved its center. I rescaled it to a different size. If it was a different model, I mean, if you rotate it around its center, it doesn't, the rotation actually, since the sphere is symmetrical in all 3 dimensions with respect to its center, rotating it around its any axis that passes around it, you will not see any difference unless it has a texture on it. Like if it has an earth texture on it, rotating the sphere is going to have some effect. But if it has a fixed color all around it, rotation will not do anything. But these are the transformations we will talk about. Moving, which we call translation. Translation here means the translation transformation. Translating a sphere means it moving the sphere. So adding or subtracting some values from its center. This is what translation is going to mean. Rotation with respect to some axis, and scaling again with respect to some pivot point. We are going to talk about these things, and this is how we can have our virtual world. Now let's get a new slide. Now imagine we have a virtual world. Let's have, for example, a black sphere located at 3, 3, 3, and now with a radius of, for example, 4, And let's have another sphere here with a radius of 3. Maybe this one is located at 6 minus 4 and 8. Okay, I'm just making up these numbers. Okay, with a radius of 3. Okay, imagine this: all of your virtual world is composed of these two spheres. Then you're done. You have done modeling your virtual world. Now, let's take a picture of this virtual world. Will we be able to see this black, or we may color it blue if you want, and because if our background is white like this, seeing black sphere will make sense. Actually, we may do that, yeah. Let's use a white background. Usually, people tend to use black backgrounds in computer graphics generated images. Our last year's examples are all black background, but for the background color, you may choose anything you want. You may have like a white background color like this. That's another property we will have. So what is the background color of our image? Is it going to be white? Is it going to be black, or some other color in between? Okay, so let's have these two spheres. Now, in our ray tracing model, in order to be able to see these two spheres in this 3D world, there's another very important thing that we need to have. We need to have our eyes, our camera. Okay, so for example, if you take a picture from this angle, the spheres look different, the black one to the right of the red one. But if you take a picture from this viewpoint, the right one is to the left of black one. So just, although I'm drawing these two spheres on this whiteboard, from some, actually we're also, the way I'm drawing these things, I'm looking at these spheres from a point of view, because I cannot really have a three-dimensional, for example, if I could have these real objects with me, you're still seeing when they're in front of my camera, you're seeing it through the eyes of the camera on a 2D projected screen. So, but just imagine that I just gave you this textual information in Notepad++. I just told you that. Two spheres. One of them is at 333, radius of 4, it's black. Or maybe let's make it blue. And the other is at 6 minus something, minus 4, 8. 6 at, so minus 8, 4, right? Minus 8, minus 4, 8. Minus 4, 8. And its radius is 3 units, and it's red. Okay, if I give you this information only, and that's what our virtual world is right now. How are we going to take a picture of this virtual world? One important thing is to have a camera. Where are we going to? We need to have a camera to look at these things. So the camera is defined in many applications, in OpenGL and in our ray tracing application. We are going to define the camera with these parameters. This part is really important because it will help us to make up the image plane with the camera. So the camera is actually a system of that consists of a focal point, an image plane, and an image window with virtual pixels that are located in front of the camera, within the camera. Okay, so the way we are going to indicate the camera is going to be this. The one important thing is going to be its position. The position of the camera, which we will use it. Sorry, my phone is ringing. The position of the camera is going to be given to us as a 3D point in this virtual world, again in world coordinate system. And so, for example, where should I locate this camera so that I will be able to see them? So I will try to code this, write some code to actually see these things. Maybe we will not be able to finish it today, but I will just take a note of our spheres location, camera location. But certainly on Thursday, we will have our Thursday lecture at 11:40. I will write some code so that we actually generate these images of these two spheres. Now, one of the first bugs of a first-time computer graphics programmer is to get black screen. Okay, and sometimes you get black screen because of different incorrect placement of the camera. I mean, this is a huge infinite world with two spheres in this infinite world. It's really easy to set up your camera to look at a location like this. Okay, in that case, you generate an image in front of it. What do you get? You get a black screen. So being able to see those two spheres, both of them on the same image, you have to be very careful about where you're going to place your camera. But as I said, you're in a 3D world, you can look at different directions, and it's an infinite world that you place your camera in, and there are two spheres that are in a very specific location in this 3D world. Okay, so you have to be very careful on where you place those cameras. Usually, one thing that you can do is, by default, for example, in OpenGL, the camera is placed at 0, 0, 0, and the placement of the camera itself is not sufficient because we also need a looking direction. Okay, so my camera, my head may be in the same location here without changing it. Where you're looking for, whether you're looking to front or to left, to right, or behind, is determined in addition to this central point of the camera. Sometimes this is called eye point, or given just as eye, or sometimes E is equal to this, or origin O is equal to this. So this is where the camera is located. This is the focal point. The reason we have a position for this point is it will be the focal point of the light rays that merge. So it will be our focal point, and it will be part of our camera system. But it will make sense with a gaze vector. So this is indicated. So here, let me write it, a gaze. So we need a looking direction. Okay, a camera, a looking direction, camera focal point, a looking direction. Is this everything we need for the camera? Let me just show you how I have another degree of freedom to indicate my viewing direction, or the image that is going to be formed. There are also other parameters about where the image plane is located with respect to the eye, but there's another degree of freedom. So I position my head in some location, I fix my gaze in some direction, and then I have another degree of freedom. Look at this. I can, without changing my gaze, if you look at the tip of the pen, it's not changing. It's still looking towards the camera, but I can move my head left and right. So this other thing that we need to fix the camera's gaze and looking direction is what is called an up vector. Okay, this is my gaze, and this is the up vector and my camera position. So if you fix the up vector to some value, the camera is fixed. Okay, these are called as extrinsic parameters. It's external parameters. It becomes fixed if you just also say my up vector. So this up vector and the gaze vector are actually, they have to be orthogonal to each other, because this gaze is going to be the minus z-axis of the local coordinate system of your camera. So the way we define our camera, you can easily imagine that it's like some local coordinate system with the eye point or origin. That's why I think it's called O sometimes. It's the origin of the camera. It's the origin of the local coordinate system of the camera. Why do we have gaze as minus z-axis? That's also just convention. Why don't we have, for example, gaze to be x-axis? Because since this up is easy to be y, it's easy to have this x-axis as the gaze, but this is just convention. People, the local coordinate system of the camera, let me use a different color for that too, is usually defined like this. If this is the x-axis of the camera, the up vector is your y-axis of the camera, and this is the z-axis of the local. So this is the local coordinate system, or sometimes named as viewing coordinate system, VCS, viewing coordinate system, or camera coordinate system. So this is V, okay? Viewing coordinate system is what we have as the camera origin, the gaze direction, and the up vector. So if we have the gaze and up vector, this x, y, z camera axes can be determined from gaze and up vectors. Okay, so gaze up and this e, these both of them, this gaze, e, and up, what are they? They are three-dimensional vectors. For example, e is going to be, let's give some values to gaze, up, and e so that we'll most likely see these spheres. My guessing is not that good. Probably when we use these values that I'm going to make up right now, maybe we are going to see them in an angle that we don't want. Maybe just we are going to see the top of them, top of the spheres, maybe just from the side. I'm not sure. So it's really difficult to. So let's try to imagine where they are. So in order to be able to see them, I need to, my E has, I think, if I'm looking at this direction, if the Z value of E is larger than, for example, 3 and 8 here, if I place it as like at 15, so in terms of Z value, it's like I'm away from these. And if I maybe put the E value, so this is, sorry, the height of these things, one of them is at 3 and one of them is at -4. If I put the height of the camera at 0, I will be just in the middle of these two things. And 3 and 6, maybe I should also put my camera in between 3 and 6. Maybe, what about 5? What about this positioning of the camera? 5, 0, 15. So it's far away in the Z direction. And if it's looking at, for example, so this is what I'm going to give to the location of the camera. So as you can see, although in the viewing coordinate system, in its local coordinate system, according to the camera, this is its origin. This is the 0, 0, 0 of the camera. But when I say E is at 5, 0, 15, which coordinate system I used to have these values, 5, 0, and 15? I used the world coordinate system, right? So these values of the camera, the position of the camera was given in world coordinate system. So let's have them as 5, 0, 15. So you see how so angle of vision, there is a factor that exists to indicate this is not the entire camera. We didn't place the image plane yet. So this angle of vision, it's also called the field of view angle. It's not the actual correct term for angle of vision is actually field of view and angle. Sometimes this field of view is, you may see this acronym FOV. It means field of view. And there are two field of view angles actually, both horizontal, for example, the horizontal field of view and the vertical field of view. It determines how, and this is really important, right? I mean, if you have a wide horizontal field of view, both of the spheres are going to be within, we'll be able to see them. In both, so it depends really on our field of view angle. So what will determine our field of view angle? I'm going to be using a different slide for that, but let's have, for example, this is our eye position. Let's have our gaze simply looking at the minus z direction of the world too. So what I can have is, I can have my gaze vector to be 0, 0, minus 1. And I could have my up vector to be also upright. I don't want tilted images maybe. My up vector here, I may also want it to be 0, 1, 0. The same vector as the world coordinate system y-axis. So my up is aligned with the world coordinate system up, so that I see everything. This is something really natural, right? I mean, if you think the surface of the Earth as local around you, the surface of the Earth is like flat. If the y-axis is the axis from the Earth's surface, if it's the normal of the Earth's surface, we usually, since we are upright creatures, we usually see the world, also our view is aligned with the Earth surface's normal vector, which is this y vector. So having up 0, 1, 0 makes sense. Now, I have specified the camera position, I have specified my up vector, gaze vector. We are looking at minus z direction of the Earth or of the world coordinate system. This will make the u of the x-axis of the camera will also be aligned with the, so our actual orientation of the camera is entirely aligned with the world coordinate system orientation. Okay, but our camera is actually at a different position. If it's not at 0, 0, 0. Okay, now let's come to the second part, which will actually determine our field of view angle. Where's the image plane? First of all, if we assume that all the light rays in the scene, so let me now, maybe we can, yeah, again, I'm going to do some kind of a perspective viewing of this I vector. So this was this x, this is this up vector, and this is our gaze. So gaze is actually, so this is the gaze. Gaze is the just inverted negative of the local z-axis of the camera. All right. So you may have lots of questions at this point saying that why do we choose gaze to be the minus z-axis of the camera? Again, this is just a convention, okay? And people use it. People just try to say, okay, I'm looking at this direction. This x-axis has to be towards my right and up vector towards my left. So this in the right-handed coordinate system where I'm looking becomes the minus z coordinate. This is some in an arbitrary choice. This choice this choice was made, and this is just the convention people use these days. So this is my E value. Now, what I'm going to do is I'm going to now, since all the light rays, I'm going to have the light rays red. Light rays, actually let me just originate the light rays from here, but they're coming to this, the point E is the focal point of the light rays that I'm going to have. Okay? Now, imagine all the light rays are coming to here. Now, what I need is, in order to collect these light rays, I need an image plane. And this image plane, if it is, for example, there's some singularity here, the image plane cannot be the same as XY plane here, because there will be no light rays collected at all. So there will be a single point on that image plane that we see. So here, let me just erase these things to make it now the image seem clear. Now we are going to have the image plane at some distance. So how am I going to do it? Like this, maybe. Yeah, a bit inclined, not that much inclined. It should have the same inclination as the X, maybe like this. Yeah. Look at this. It's not exactly center. So my drawing is really bad. Sorry about that. it's not that I'm using the mouse. It's not the reason that my drawing is bad. If you were in the classroom face to face, I would be drawing on the blackboard with the exact same quality. So so what happens is that so this gaze, actually let me just first, yeah, I think it's better to do it this way. This is like a center of what I want to draw. Yeah. So imagine this is the center of our gaze. So what we are going to do is we are going to determine, we are going to have an image window that is placed in front of our camera with a certain distance. So this distance is really important as to our field of view. Let's call this distance D. Okay, from E to the center, to the point where our gaze hits this image plane. Actually, there's this plane that you see here, the entire plane that this image window is placed upon is going to be a plane which is parallel to the XY plane. That's another convention. We can actually have tilted planes. That's also possible, but we are going to assume that our gaze intersects this plane at right angles. So it's actually, this is parallel to the XY plane. So we have an image plane parallel to the XY plane. Assume that this is the image plane itself is certain distance. Just imagine a plane which is parallel to XY plane, which is moved certain distance away, d distance away from our camera. Now, think about what will happen. Oh, by the way, we can have at that same d distance away, the plane is infinite, right? We could have an image window which is actually larger than this one. Why did we design it the same d distance away? So this may also still be d distance away. Let me try to. So imagine the red window and the black window are exactly on top of each other. So this one is also d distance away from this. But as you can see, it's of larger size. So there are two issues here. So it will have a larger field of view, but in order to get a larger field of view, our only option is not only to increase this image window size. This may, for example, the size of this image window will be given to us in units of the world, for example, or sometimes the left and right boundary can be given to us. Maybe you may be saying that in the left boundary of the image window is at -2. At x is, this means that it's at x is equal to -2. Then we are going to focus ourselves only on symmetric image windows, in which if this is given as -2, the right boundary of the image window will be at 2. The top may be, for example, at +1, and the bottom may be at -1. So we have a rectangular image of size 4 by 2. Okay, so this is its width, this is its height, so this is width, this is height, as you can see, a 4 by 2 image, a nice landscape, rectangular landscape orientation. And the other window, for example, could have a different setting, saying that its right boundary is at 4, its left boundary is at 4, and this one is at 2 and 2. So it's a larger window, 2 and -2. It may be an 8 by 4 window that is exactly the same distance. This d distance, for example, let's let d to be equal to, for example, 2. Okay, let's have this d distance equal to 2, and these are the boundaries of our image window. So with these settings, actually, I can have which light rays are going to be, by shooting light rays from my eye point to my image window that pass through my image window, there's a specific point that these light rays intersect. I mean, for example, you have this E, you have your gaze direction. If you just select a point here on this image window, there is a single line, there's a unique line that passed through this point and this point, right? So if this was my single pixel, and if you think about this single point as a very small field pinhole camera, there will be a specific ray that will pass through the center of this pixel and also pass through this focal point. Okay, we will actually compute the equation of these rays after we set up our pixels on the given image window. So if the image window's boundaries are given to us, like this, for example, we will be able to compute, for example, let me ask you this. What is the coordinate of this top left pixel? Can we compute this? Given that, consider the red window with these boundaries. Let's use the red one for our cases. So let me also write them down. So we have our virtual world. Now we have our camera set up. Camera was at this location. So this is the camera location. My gaze is, to make it easy, I just choose vectors that are aligned with the world coordinate system, but we're going to come up with equations which can work with any arbitrary gaze, any arbitrary up vector, and in any condition. So we are going to, in the ray tracing geometry slides, there are derivations of equations, which the first part is computing the coordinate of these pixel centers given two values. For example, if I have an image window, by the way, after this -44, -22, which was given in the world coordinate system, another thing I need to give is, in order to generate an image, in order to generate a discrete image like this, I need to also know the resolution of this in terms of how many pixels do you want to fit in this 8x4 area in your virtual world. I have an 8x4 area, 32 unit square area. For example, can you fit here 32 pixels only? Okay, does it mean that I have a 32 pixel image if I choose these boundaries? No, right? I mean, since this is not an integer space, our real world is not an integer space. You can have pixel width equal to 0.001 to have 8,000. For example, if your pixels are of this size, 0.001 width and height size pixels, what does it mean? In an area from 0 to, from -4 to 4, the distance is 8, you can fit 8,000 pixels here in this width and 4,000 pixels in this height. So it really depends on what resolution you want to. So pixel, if your pixel size is less than that, for example, if it's this, it's going to be half as much. Okay, so here another parameter that we want to specify is what is the resolution of our image. The resolution actually usually is not given in terms of pixel width and height. Usually we are given, for example, I want to generate 2000 by 1000 image. Okay, now what happens if you say, for example, I want to generate a 2000 by 2000 image. I want my image to be square. But my image window was not square. What will happen? Your pixels are not going to be square pixels. It's like you're going to be stretching, since this is the real world window that you're looking into your virtual world. I mean, this image plane is something that you look into your virtual world. If the aspect ratio of this, aspect ratio is the ratio of width over height, or vice versa, I don't remember which one was which, but it's basically the ratio of width to height. So this one has an aspect ratio of 2 if it's width over height, okay, 8/4, it has an aspect ratio of 2. But if you specify a resolution with a different aspect ratio, like this 2000 by 2000, it has an aspect ratio of 1. what you will be doing in effect is like you're stretching what you're seeing. Your spheres are going to be seen like ellipsoids stretched in one direction. So it's usually good in order to avoid these distortion effects, these stretching effects. It's good to have a resolution of the image which has the same aspect ratio of your image window here. So since it was an 8x4 in terms of size, let's have a 2000 by 1000 image. So what it means is that 2000 by 1000 image. So we are going to draw 2000 in one row. We are going to have, so the distance from here to here was 8, the unit was 8, and we are going to have 2k pixels in this 8 units. So what is my pixel width? It's 8 divided by 2000 is my pixel width, right? How did I find that? I know that my image window occupies this space from -4 to 4. I was given the left and right boundaries. Let's also write them up. So this was about the camera. Now the camera is a system which has a, for example, distance to eye is 2 units. Left boundary of the image window, so distance to eye. So this is about the image plane. So let's call it image window, because the plane, when you say image plane, it's the infinite unbounded plane which is parallel to x-axis. So image window distance to the eye is 2 units, and also let's note that it's parallel to the xy plane of the camera. And its left boundary is at -2. We can write it, its left boundary is at x is equal to -2, right? Or it was -4, right? We decided on the larger window. Left boundary, since it's symmetric, we can have right boundary at +4, bottom boundary at y is equal to -2, and top boundary is at y is equal to 2, and its resolution is this. Okay, so this thing that I defined here, these values, it's a complete system of a camera that I need to be able to view these two spheres in the virtual world. Okay, now with this, I can find my pixel width. Now, let's try to ask this question. Since we are out of time, I'm going to leave this as an exercise, and we will start. I may actually save these images, and we may just continue from here on Thursday. Our first task is going to be this: what is the coordinate of this top left coordinate of the center of the pixel at the top left? Okay, so what is this point here? If I find this point, I will be able to generate a ray from E to this point. There will be a single line, a unique line that passed through these 2 points, and then I may have this line get intersected with my objects to see whether it's going to be blue or red or the background color. And in general, the first problem we will try to find is this. These pixels on the image, they are, when you identifying a pixel, a particular pixel on an image, actually you just need 2 values. Since this image is like a 2-dimensional array, ij, if I change I and j from 0 to 2000, so was it a 2000 by 1000 image? Yeah, 2000 by 1000 image. If I changes from 0 to 2000 and j changes from 0 to 1000, okay, so by the way, I now see, unlike regular array representation where the first index shows the row, here I shows the x-axis, it means this shows the column. Therefore, there are 2000 columns here. I changes between 0 and 2000, j changes between 0 and 1, and they are integers. So my image coordinate system is actually an integer coordinate system, which you indicate a pixel like the pixel 500, 200. When you say the pixel 500, 200, so it's somewhere here, 200 is somewhere here. You may be referring to this pixel here. So our goal will be, given ij, given the pixel value, pixel coordinate 500, 200, what is its pixel center coordinate in this camera setting in our world coordinate system? So we will find ourselves some xyz values, let's call them px, py, and pz, which will be the center of that pixel while this image is located. So this is really nice geometric problem, which is not very difficult to solve actually. In our case, for example, so probably you find the top left correctly, most probably 3.996, 1.996, and -2. Very good. It's actually it has to be, since our gaze and our up vector, they are all aligned with the world coordinate system. We already know its z-coordinate, right? The z-coordinate of all the pixels have to be at -2. Okay. Now, because our system is aligned with the coming with the coordinate minus, or is it really -4? Did you forget that this e is actually at 5? So it's not. The center of this image is not at 0, 0. So this probably it's not at -3.996, because this -4 is relative to the camera coordinate system. So that was another thing that you should be careful about. This left boundary, right boundary, bottom boundary, everything here, the camera position, camera gaze, camera up, it was given with respect to the world coordinate system. But when I was talking about, no, you don't need to be sorry. So it's a very good point that you actually did that, because it's really confusing, because we were giving everything in world coordinate system, but when I was giving left and right boundary, bottom boundary, I didn't take a specific note about this, but when I gave them, I assumed that the center of the image was at 0, 0, 0, right? So this was like given to local camera coordinate system. So taking into account that, we will be able to find this coordinate. But still, it will be, you just add 5 to that, right? I mean, since our camera has moved 5 units to the left, if you just add 5 to what you have found, the x coordinate, its y coordinate was 0. So if you just, and also it was at 15, right? So if you just add 15 to your z coordinate, it will be, since its z coordinate is 15, since it's 2 units away, actually the z coordinates of all the pixels here, they will be 13. So you just need to, the only thing we need to do is add the camera position to the solution you have found, because it was just a translation of the camera. But when you rotate the camera, if you have an arbitrary gaze vector, these equations will not be so easy to come up. I mean, the pixel coordinates, but it's still not that difficult. We will find the pixel coordinates for any arbitrary orientation of gazes and things. But this is a really nice geometric problem, right? I mean, every time I talk about this problem, it's not so difficult in terms of mathematics, and it's very fun to do. All we need to, the first thing in your ray tracing program, also in your assignment, the first method, the first function you will write is this. Given a pixel, you will have your main code is going to be like this. For I is equal to 0 to 2000, for j is equal to 0 to 1000. Okay, so what is this? What are these two for loops? For every pixel. So this is basically for every pixel. So this is the whole entire ray tracing code will be inside this main loop. First you need to do is, for that particular ij you have in this for loop, you generate the ray. Find the pixel coordinate. So let's call it PC, or pixel coordinate. Pixel coordinate is equal to find ray ij. Okay, that's the first line you will be writing. So find the ray that passes through the ij pixel, and this will be the first problem we will be doing. After we find this ray, the pixel coordinate. We have found this straight. The next thing is form line between E and pixel coordinate. And this is not going to be so difficult. I'm given 2 points. I'm given E and the point P here. How can you construct a line that pass through these two things? In parametric line equation, we will be writing this. The line that we will be forming, I will parameterize with respect to some scalar value t, is going to be just E times P minus E times t, not E times, E plus P minus ET. So this is the equation of the line. When t is equal to 0, what happens? You're at here. When t is equal to 1, what happens? You're, by the way, this L, E, P, E, and this L itself, everything here in this equation are three-dimensional vectors. The only thing that is scalar is this t, which is our single parameter. Actually, a line in 3 dimensions is a one-dimensional object, which means that any point on this line can be uniquely identified with a single value t. So when t is equal to 1, just put t is equal to 1 here. E plus P minus E, it's just you're at P. If t is equal to 0, you're at E. So this will be our line equation. Sorry for taking 5 minutes of more of your time, but these things get me excited. It's really simple, but it's really fun to derive these equations. And this is you are going to form the line, intersect the line with the objects, and assign the color to that pixel. That's your entire ray tracing algorithm. Okay, and assigning that color, we will do some more calculations, the interaction of the light rays with the object's material surface, but basically that's it. How we construct shadows, how we come up with reflections. It's just small modifications, additions to this main loop. All right, that's it from me for today. I will stop recording now, but I will stay here.